you see can you see a big title page, or can you see the PowerPoint?
I can see the small part of your screen, Pat.
So we were seeing the whole picture, whole screen, Pat. Now you have the split one. Next slide as well on the right.
So you're not getting the right one. Okay.
No. YouTube is working, Marco.
Sorry?
YouTube is working.
Excellent. Super. Thanks.
So I need.
So initially when you showed Pat, we were seeing the whole thing.
Yeah.
That should be better now. You should see. You
Yeah.
should just see us.
Yeah. Yeah.
Yeah. Right now.
I've got a slightly strange setup with 3 screens in my lounge, all running off my laptop. So yeah, anyway, there we go.
Are you in UK, Pat, or Chile?
No, unfortunately, I'm in the UK. I'm
Okay.
I'm learning to live in my own house, which is a very strange experience for me.
Yeah. How are things in UK? University is closed, I'm assuming. Do you have any lab work going on, or?
The university is, of course, fully open. Our buildings are closed. So we're still teaching, we're still doing research. Most people are still working. It's just we can't go into the buildings.
Yeah, same here.
So I have a big problem with people say the university's closed when it's not.
Yeah.
So we're I mean, Nottingham is in a good position. So last week I think there was only 10 hospital admissions due to COVID-19. So we're currently planning to get people back in the labs, social distancing and all that kind of stuff, but get people back in the labs actually doing some practical work.
Yeah, our also university banned using of social distancing. In Wisconsin, we are supposed to use physical distancing from now on because they encourage social activity, social connections, you know, so that's funny too.
We still call it social distancing here, but yeah, so hopefully by the end of the month, we'll have some people back in the labs.
Sure.
I can't see us being back in our offices until September, October. But to be honest, it doesn't matter. It's more efficient not having to commute.
Yeah, actually, we save gas, right? We don't burn, you know, fuel gas if we are driving with a fuel car.
Yeah, and the meetings are shorter. When you can control who can talk, that's quite useful.
Yeah, I agree. How is the China campus you have? Is that also similar?
No, they're back teaching in classrooms, everything. So they came back 4 weeks ago, something like that. So there's some restrictions and face masks and all that kind of business, but no, essentially the China campus is operating normally.
That's good.
They're about 2 months ahead of us, so you kind of expect that.
Yeah.
And they do controls in a slightly different and slightly more efficient way. So so yeah, there's a lot of control and stuff like that apparently, but it's
it's good to hear that at Nottingham you don't have too many cases. You know, that's great.
It's really interesting. Derby does, but Nottingham doesn't. So for those who are listening who don't know, these are 2 cities that are 20 kilometers apart.
Oh, I see.
And so Derby has a lot of cases and Nottingham has very few. It's interesting.
Yeah.
And a lot of it's to do with the universities, because Nottingham receives a lot of students from elsewhere in the country, whereas Derby sends a lot of students to elsewhere in the country.
Sure.
Universities sending all their students home was probably not the right thing to do when you begin to look at it a little bit carefully.
What about the fall semester? Do you think students will be able to come back, or international students, newly accepted students, will they be allowed to get into the country, or there are challenges?
I have no idea.
It's too far away.
Yeah, and not my problem.
Yep.
But Marco, what's the okay, I think you might be about to tell us. I was going to say what's the plan in terms of time?
But we will start in 5 minutes.
Okay.
I will give a short introduction for all of you. Later, you will be your presentation for almost 20 minutes. And after that, we will have a round of questions between the audience and all the panelists and you.
Okay.
Okay. We are still accepting people that are connecting to Zoom, so let's wait for a while. Okay, good morning, everyone, or good afternoon, or good evening for some of you. My name is Marco Rivera, academic from the University of Talca. Welcome to the second session of the online meetings of the Energy Network. I would like to thank you, everyone, for being participating of this activity. And while we are waiting for the other people that is expected to join our meeting, I would like to ask you, give your name and where you are coming from, okay? Jose Elizondo, can you start, please?
Hello, everyone. I am Jose Luis Elizondo Carrales. I am from Mexico. I work with Marco since 2009, and I am pleased to be here.
Thank you. Diego? Diego, your microphone.
Sí, buenos días, Marco. Buenos días a todos.
Hello.
Diego.
Buenos días.
Hello, my name is Diego. I am a student doctoral. My professor is Marco Rivera. Y nada, hello.
Thank you, Fernando.
Hello, my name is Fernando Briz. I'm a professor at University of Oviedo in Spain. Hello to everyone.
Thank you. Cristina.
Con respecto a la reciente difusión de un video sobre una supuesta...
Hola, buenos días a todos. Gracias por participar. Hello, everyone. Thank you for coming with us. And
Thank you. Claudio.
Hi, everyone. I'm happy to be here just to listen this meeting. And I hope we will have a very nice discussion on this interesting topic.
Thank you. Pat.
Me. Pat Wheeler. I'm a professor at the University of Nottingham, and I'm looking forward to giving a short presentation this afternoon.
Thank you. Ariel.
Hello, everyone. I'm very happy to be here. I belong to University of Talca. I work with Marco Rivera and Cristina Bow. And I will be the person to ask the question later to you, Patrick, and to the...
Hacer el pedido a TI, capaz que lo quieren ver.
María. Thank you.
Hello, I am Maria Ines Bala from University of La Plata. Listen to these interesting talks.
Thank you. Janet.
Hello, everyone. I'm Janet Diaz. I'm a journalist of Macrofacultad, and I'm working with Marco and Cristina and Ariel.
Thank you. Ismael.
Hello, good morning. This is Ismael Araujo from Mexico City, from the National Polytechnic of Mexico. Thanks for the invitation.
Thank you. Pablo.
Hello, good morning. This is Pablo Cosuta from Instituto Tecnológico de Buenos Aires, ITBA. Thank you for the invitation.
Thank you. Bulent.
This is Bülent Şarlıoğlu. I'm from University of Wisconsin-Madison. I was in your beautiful country, I think 2016. Marco, please correct me for
17.
Which year?
17.
17 for SPEC in Porto Varas with my student Pablo Castro. So I had really good time, and thank you very much for the invitation, Professor Marco.
Thank you. Lucero. Okay. Camilo. Camilo González.
Yes, I'm Camilo Gonzalez from Duoc. I'm recently graduated at engineering in electrical and automation.
Thank you. James Lady.
Hello, my name is James Lady. I am an academic from the University of Talca. Thank you for the invitation, Marco.
Thank you. Antonio. Antonio.
Hi, my name is Antonio Cardoso. I'm a professor at UBI University in Portugal.
Thank you. Vladimir Muñoz. Vladimir.
Hi, everyone. I am Vladimir Muñoz from Universidad del Biobío. Thank you.
Thank you. Daniel Ramírez. Daniel.
Good morning. It's a pleasure to meet you. My name is Daniel Ramírez. I'm from the University of Valparaíso in Chile. And well, my research area is focused in electrochemistry for energy purposes and photovoltaic materials, new photovoltaic materials.
Thank you.
Nice to meet you. Thank you.
John Kay.
Good morning, good afternoon, good evening. I'm John Kay. I'm with Rockwell Automation in Canada, and I'm a principal engineer for the medium voltage business looking at new technologies.
Thank you. Welcome. Felipe Herrera.
Hello, everyone. Good morning. My name is Felipe Herrera, and I am a master's student at the University of Chile. Thank you for the invitation.
Thank you. Han Lin Dan from China.
Hello, everyone. My name is Han Lin Dan. I come from Central South University. My research field is motor control and matrix converter.
Thank you.
Thank you very much.
Rene Dominguez.
Hello. You listen to me?
Yes.
Nice to meet you. I am from Mexico. I'm a researcher in optics, and it's a pleasure to be in this meeting. Thank you very much.
Thank you. Marcelo.
Good morning. My name is Marcelo Cortés from University of Antofagasta in Chile. Thank you very much for this invitation. I'm reading from Antofagasta.
Thank you. Welcome. Laura Sanchez.
Hello, I'm from Paraguay. I'm a professor at the Universidad Nacional de Asunción. Nice to meet you.
Thank you. Bernard.
Hi, Marco. Hi to all. Bernard Jara from Pontificia Universidad Católica de Valparaíso, Chile. Thank you for this invitation.
Thank you. Thank you. Victor.
Hello, my name is Vitor Monteiro from the University of Minho, Portugal. Thank you very much for the invitation.
Thank you. Beshan Rahuma.
Hi, I am Wissam Rahuma, University from Texas A&M University at Qatar. Thank you very much for your invitation.
Thank you. Thank you. Federico Rivera. Okay. Diego Valencia.
Hi everyone, my name is Diego Valencia, McMaster University, and last year PhD student working on electric motor control for electrified powertrains in Dr. Ali Ahmadi's research group.
Thank you. Manuel Martinez.
Hello everyone, I am a PhD student from the University of Chile, and I expect to continue my studies with the University of Nottingham in this year.
Thank you.
Thank you for the invitation.
Marina.
Hello, hi everyone. Hello, Marco. My name is Marina Sanz. I am associate professor at Universidad Carlos III de Madrid. I'm working with Power Electronic Systems Group. My research area is related to modeling and control of power electronic systems. Thank you very much for the invitation.
Thank you. C. Vidal.
Hi, my name is Carlos Vidal. I'm from McMaster University, Canada.
Thank you. Jerko Franulic. Daniel Goretti.
Hello, I am a PhD student at the Mechanical Engineering Department in McMaster University, and also I'm a Chief Engineer of Electrified Propulsion System in a big OEM.
Thank you. Sergio Sarda.
Hi, Marco. Hi, everyone. I'm Sergio Cerda. I work in Marcos University in the Technological Transfer Department.
Thank you. Aung Bu Hu. Marcio Rodriguez.
Hello, everyone. I'm from Brazil. I'm professor from Federal Institute of Southeast of Minas Gerais in Juiz de Fora. Nice to meet you.
Thank you. Thank you. Federico Rivera.
¿Algo más? Sí. Hablando acá, ¿cómo está? Buen día a todos.
Hello, my name is Federico Rivera. I am a student de Universidad Tecnológica de Pereira.
Thank you. Gerardo Romero.
Hi, Marco. This is Gerardo Romero from Reynosa, Mexico. I am a professor of the Autonomous University of Tamaulipas, and my research area is on control systems. And thank you for the invitation.
Thank you. Giselle Silva.
Good morning. I'm here to Brazil. And, I'm sorry, internet is horrible. I have to.
Thank you. Alejandro Garcés.
Hello, good morning. My name is Alejandro Garcés. I'm happy to see many friends, Marco, Patrick, Marinés. I'm from Universidad Tecnológica de Pereira.
Thank you. Sergio Toledo.
Hello, everyone. I am Sergio Toledo from Paraguay. I am PhD student at the University of Talca, and my supervisor is Professor Marco Rivera. And it's a pleasure for me to share with you today. Thank you.
Thank you. Jonathan Gonzalez.
Hi everyone, I'm Jonathan. I work in administration, and also I teach economics at the University of Talca. Nice to meet you.
Thank you. Adolfo Hidalgo.
Yeah, hi. My name is Adolfo Hidalgo, and I'm a student of mechanical engineering here in the University of Talca, Chile.
Thank you. Pablo Yáñez. Ricardo Pérez.
Hello everyone. My name is Ricardo Perez. I'm PhD student from the University of Talca. I'm glad to be here.
Thank you. Matías Díaz. Constanza Ahumada.
Oh, hi everyone. Hi Marco. Hi Pat. So I'm assistant professor from University of Chile, and it's nice to see you again.
Thank you. Efraín Ibaceta.
Good morning. My name is Efraín Ibaceta. I'm a student at University of Santiago of Chile, and with a bachelor and master.
Thank you.
Coursing. And I focus on in modular multi-level converters, especially in modular multi-level matrix converters. And my supervisor is Matias Diaz.
Matias Diaz. Okay, thank you. Ismael?
Pleasure to meet you.
Ismael?
Yes, hello. My name is Ismael Araujo from the National Polytechnic of Mexico. I work with power electronics. And again, thanks for the invitation.
Thank you. Okay. Welcome, everyone. I would like to, I'm very happy sharing with you this session. We call it Online Meeting of the Worldwide Energy Network. And if you have any question, you can use our Twitter account, TTCA Utalca, and with the hashtag winner2020. Ariel will be collecting all the questions, and at the end of the session, presentation of Patrick Wheeler, we will be asking to the panelists and also to Professor Wheeler. Okay, Professor Wheeler, in order of the time, I would like to give you the control of the Zoom platform for your presentation.
So hopefully you can hear me and hopefully you can see a presentation. Is that correct, Marco?
Yes, correct.
Okay, excellent. So electronic systems at the University of Nottingham. For those of you who might not recognize my look, I've got a COVID-19 lockdown beard at the moment. It'll disappear at the end of lockdown, I think. What I wanted to talk about today was transportation electrification and the journey that we're on as a society to have the electrification of transportation. And to have a quick look at whether current world events are going to have any impact on that. And we'll see what the conclusion of that little look is as we move forward. Why is that important? Well, it's important. Our governments are all focusing on one issue at the moment, and it's important to remember that other things do continue. So I work at the University of Nottingham, where we do a lot of work on transportation electrification and energy conversion. We've got a very large research group, currently about 160 people or so. And we work across the areas of electrical machines, power electronic systems, motor drives, and power electronic integration. All the technologies that we need if we're going to move to more electric transportation platforms in the future. And underlying all that is the thermal management, which is also very important, as we'll see. So this talk is really looking at the electrification of propulsion for transportation systems, and looking at what impact economics and indeed the current pandemic might have on these sorts of things. And so the first thing to look at is remember why we're looking at transportation electrification. And this graph shows it very well. This looks at carbon emissions over the last 30 years, looking at fossil fuels, so all the petrol we burn, all the coal we burn, and so on, and looking at the effect that world events can have on that. If we take the first circle first, 2008, there was a big global financial crash. All our finance systems had problems, and we actually had a slight downturn in the emissions. What was interesting is if you look at by 2010, we'd recovered, and the growth in carbon emissions took about 2 years just to get back to its normal line. If you look at what's predicted for COVID-19 at the end of that, so looking at the carbon emissions in 2020, you'll see that the maximum drop is about the same magnitude as that financial crash of 2008. So we're not looking at a massive impact on our carbon emissions just from the lack of economic activity we have at the moment. It's about the same as that financial crash 12 years ago. That's not my figures. Those are figures by various economists that have been put together. But it's an interesting range, and that little red triangle you can see is the range of predictions. The other thing I thought it was worth doing was having a look at how long other pandemics have caused an economic slowdown, and just in parts of the world. So this is quite a telling picture. So that red line you can see there with a massive dip is actually the impact on aviation, on flights of aircraft from SARS. And it's worth noting that that scale on the bottom is in months. So basically 6 months after the pandemic of SARS started in Asia, the number of flights in Asia was back to its historical norm. So we're talking there, okay, it was a big pandemic for that part of the world. It had a very similar lockdown in Asia as we're seeing globally now, but we saw a very, very quick recovery. And there's various other SARS, MERS pandemics there, all coronaviruses, so all with a similar characteristics to COVID-19. Okay, they didn't come around the world in the same way, but it shows how quickly the economies and indeed, in this case, aviation can recover. So we're looking there at something that lasts months. Then I thought the best thing to do was to have a look at what roadmaps we're on in terms of transportation electrification. Where are we in the industries which are looking at this? I thought I'd start with automotive because that's the one which affects us most every day. Most of us will have cars or use petrol or diesel-based transportation systems. And it's quite interesting to look at the roadmaps and where people think this industry is going. So you'll see there that today the majority of cars we're using are petrol, gasoline cars. This chart starts in the year 2000. And by 2035, most countries are saying that they're not going to sell new petrol or diesel cars. So you're seeing quite a turn down in petrol and diesel cars over the next 10 to 15 years, as you would expect to see. And then those cars will obviously last 10 to 15 years, which is why petrol and indeed diesel, which is that dark grey colour on this plot, will decay out sometime around 2040, 2045. Obviously, if the economics are correct, the growth in transportation will increase. And so we have to replace those diesel and petrol vehicles with something else. I think this chart is hedging its bets a little bit between hydrogen and all electric. By electric here, it means battery powered. And it's suggesting a roughly 50-50 split. I think one of those two technologies will win. But what's interesting to see on here is you're also getting hybrid gasoline plug-in cars, you're getting hybrid diesel vehicles predicted to still be running and still be a major part of the mix of vehicles into the future. What's really interesting to me is the fact that when you get to 2050, there's a number of different colors there. We're not looking at a car industry or truck industry that is relying on one fuel and one system. We're looking at different vehicles, all of which will have different characteristics and running on different fuel sources. Why is that important? Well, if you choose to do research and development in hydrogen powered cars, electric powered cars, or hybrid systems, there's a feeling that you've got to back the right horse. We've got to be looking for the right solution that will end up being the dominant fuel source in the way that petrol and diesel have been for most of the last 100 years. What this sort of prediction shows is that there isn't going to be one fuel source, there isn't going to be one solution, and that we're actually going to have more of a mix, possibly based on the duty cycles and the use cases we have for those vehicles. So in the same way that you might have a small town car and a larger car for working on the land or for doing long motorway journeys, we're seeing exactly the same thing with the fuel source. You might have an electric car for doing your local journeys, but a hydrogen fuel cell vehicle might be more useful for traveling long distance. So we're looking at a very big change in the way we deal with this. This particular roadmap actually comes out of Japan, which is interesting because it's a country with a large and forward-looking automotive industry. We look back at aviation, and this is looking at CO2 emissions, looking at where the industry sees things going, taking a benchmark at the 2020 emission levels. That in itself is interesting because the 2020 emission levels are going to be slightly lower than expected because of COVID-19. So if they stick with that, they've just made life harder for us in the future. And in the medium term, the aviation industry is saying we've got to have carbon trading, we've got to plant lots of new forests to try and offset the amount of carbon we're producing. But if the aviation industry is going to increase in size, and this is shown here by the big red line, showing what happens to these emissions if there's no action, i.e. we keep today's technology, they are predicting a long-term growth. Will the COVID-19 pandemic in 2020 impact on this? Probably not really. Even the most pessimistic reports I can find are looking at full recovery in 2 years. Here we're looking at a roadmap that still has 30 years to run. So those 2 years represents less than 10% of that roadmap. So will it have a short-term impact? Maybe. Long-term impact? Nah, there's nothing there that's going to worry us. In terms of how we're going to get the carbon savings and get down to, by 2040, get down to the 2020 levels of carbon emissions and then halve those by 2050, we're looking at known technologies to start with, how to make aircraft themselves more efficient, how to make operations more efficient, how to make ground infrastructure more efficient, all around the optimization of flight paths, the optimization of ground movements, and the application of things like the more electric aircraft technologies and so on. When we start looking at how to get better than that, how to start getting a reduction in the carbon emissions, we need to start looking at sustainable aviation fuels. That might be hydrogen, that might be biofuels, and new technologies. And that's where we're looking at things like hybrid electric and all-electric propulsion of aircraft. So the important thing to note here is that the goals are very long. It's going to take at least 30 years to get to this sort of position. And how we get there is something that we need to be thinking about today. Otherwise, these new technologies are not going to become available. Final roadmap to look at here is just looking at what we're looking at in terms of electric propulsion of aircraft. This will obviously be faster for the automotive industry. This is the NASA vision. The European vision is actually slightly quicker than this by about 10 years, which is an interesting difference. And this is looking over the next 30 to 40 years at projects to get up to having 10 megawatt propulsion of large passenger aircraft, maybe 300 passengers or more. So there we're looking at replacing the bulk of the passenger aircraft fleet with at least hybrid and maybe all electric propulsion, depending on the duty cycles of those aircraft. So some big challenges for the industry and some big challenges for academia. When we're looking at these systems, there isn't one system that actually looks like the right thing to do. There's lots of different ways of arranging your electric aircraft. And the first thing you have to do is to forget the systems we have today. Replacing gas turbines on the wings with some sort of battery and a motor, all placed in exactly the same place as the engine today, is a disaster. We need to look at what electric propulsion gives us and look at how we might organize an aircraft to be both very efficient, but also very safe. One thing these slides don't deal with is one of the best ways to gain efficiency is to slow down and take maybe a day to cross the Atlantic rather than 10 hours. But taking that aside, we'll leave that in the operations field. Looking at the kind of systems. So this one is looking at having a main gas turbine in the nose of the aircraft connected to a generator, but then having 3 propellers rather than 1. The 2 propellers on the wing will have a small motor behind them, operating very efficiently, and all the energy source either comes from storage or from that main propeller. If we look at other options, we find we could have distributed generators and distributed propulsion systems. So the one on the left there is a parallel hybrid architecture where you still have some gas turbines. They're still quite good at generating energy. We also got some energy storage elements there, but we've got multiple propulsion systems, maybe doing boundary layer ingestion, maybe just distributed across the wings of the aircraft and the tail of the aircraft to get the most efficient form of flight we can. Another use of a hybrid propulsion system is shown on the right. This is the kind of system they were looking at for EFAN-X, where you have your main energy source, in this case still from a gas turbine, but you put that inboard in line with the passengers on the aircraft, so it's not in the airflow out on the wing, and you use electric motors and fans on the wings for your propulsion system. Even that kind of arrangement automatically gets you a 20% increase in efficiency just because of the design flexibility it should give you in the aircraft. So there's lots of different solutions and a lot of different steps along this road. But one of the things that becomes very obvious is that we need to build very big power converters, very big electrical machines in terms of power level, but in terms of weight and volume, they need to be small. And so we've got to work on making electrical machines and power electronics smaller and lighter. One of the demonstration things that we've been looking at is to go and race vehicles. It's great fun racing things because your time from development to demonstration is very, very short. Your time to design parts of a new passenger aircraft and put that into flight can be measured in decades. When you're looking at race aircraft or race vehicles, you're looking at months, not years or decades. So one of the things we're doing is something called air race. So we're taking a race aircraft that normally races around pylons. We're taking the drive system from our electric motorbike and we're putting it onto that aircraft. A little bit too powerful for the aircraft, so we'll have to limit the power slightly. But the basic principle is to take the battery and the motor technology and see how that performs in an aerospace application, albeit with some slightly different optimizations. So we can do those sorts of things. We can demonstrate aircraft. Reasons we want to do this is so that we understand the problems more. You can see there the size and shape of the motor. It's being designed to fit in the nose of the aeroplane. We can design the batteries, the power electronics, and we can fit all that to the aircraft. The great thing about things like race aircraft and certain other duty cycles is these are slow. These are very low in terms of the time they're flying. The race time for these aircraft is about 5 minutes. So very powerful aircraft, but we're not having to have lots and lots of stored energy. We can demonstrate the technology with today's battery technology. So these aircraft, they go up, they fly, often wingtip to wingtip around some pylons. 10 minutes later, they're back on the ground. So we can do that sort of thing today with electric planes. Be great to watch, quieter, opening up new airfields for the races and so on. So lots of good reasons why we might want to do that, but also a very good platform for testing out this technology. So the technology bricks that we're going to need to make things smaller and lighter are many. From a power electronics point of view, we need to have smaller, lighter, more modular power converters that are easy to manufacture. We need to make use of the new materials that are coming online, so low loss magnetic materials. We need to look at advanced machine topologies. There's no one motor that fits all application areas. We need to understand all of those. We need to look at things like the wiring and the windings, how to get low loss rotors. Rotors are very difficult to cool, and also how to cool things, how to get the heat from where it's generated to outside the vehicle that we're talking about. So lots and lots of technologies coming there, but we can do these things. In the bottom right hand corner there is a picture of a 4 megawatt propulsion motor for an aircraft application. But that's about the size of a standard industrial 30 kilowatt machine. Technology to do these things exists today and can be used. We also need to do a lot of optimization. This example uses particle swarm, but I always say the optimization algorithm really doesn't matter. You spend years writing the scalable models of all the elements of the system, the power electronics, the filters, the electrical machine design. If it takes the optimization algorithm a week to do the optimization, who cares? It's just taking you 2 years to write the scalable models. But one of the things this does show is that the best the designers could do in terms of motor weight here was 5.5 kilos. After an optimization, just looking at the aspect ratios of the motor, the internal, external diameters and the length, that came down to 3.2 kilograms. So it's showing that with an evolution and with looking at these the optimization with an automated system rather than the designer's best efforts, we can get the motors and the power electronics down to significantly smaller sizes. Obviously, you have to do this for the whole system, not just the machine, and that's when the models become rather more complex. The other thing you have to factor in there is the power electronics. How are we going to package the power electronics? How to use different topologies in electric vehicles? This is just looking at my electric race motorbike, and in the last 4 years we've used 3 different topologies of power converter on one platform. Which one's best? Depends on which race you're racing in. So there's no great answer to that, but it's looking at building small compact power converters of the type you need in these electric vehicle applications, and showing that depending on the duty cycles, depends which type of topology for the power electronics and the electrical machine you might use. One of the other things to notice here, I mean, you'll see in the middle there is the dual bridge converter, and particularly in electric cars, there's a need to have a limp home mode. Something might fail, yes, but the vehicle still needs to be able to operate in some way. Obviously, things like silicon carbide and gallium nitride are also having an impact on those designs. And that's one of the big things happening in power electronics. The final thing I wanted to remind everyone of, particularly those in the audience in the power electronics community, we all get very excited about things like silicon carbide, looking at gallium nitride, looking at switching faster, looking at making motors smaller because we can provide better quality waveforms with higher efficiency. That's all very well and good, but to be able to make use of that, we still have to remember we need capacitors, we need inductors. When we're switching faster, we don't want pieces of wire, interconnects between the switching devices and those passive components. So the days of putting your capacitors on power planes above power modules have to come to an end. We have to start integrating those passive elements actually in the module, right down next, some of it right down next to the die, just to keep everything under control. And the example there is the voltage overshoot across an IGBT, and how you might be able to control that better if you actually put the passive components down near the device. But those of you who are observant will notice that you have to be careful how you do this, because of course you can create different resonances in your circuit. What you're seeing on the right hand side there is actually an unwanted interaction between the internal capacitance in the module, the inductance of about 5 centimeters of interconnection, and the external capacitance. So those things can lead to resonances, albeit at quite high frequencies. So the design comes right down to the optimization of the package and the fact that a short connection at high frequency looks like an inductor. So lots of things for us to think about, lots of challenges in terms of making those components smaller. So my conclusions and maybe some points for discussion is that the current situation we find ourselves in is going to cause a short-term blip in demand for transportation, but it's not significant in terms of the long-term roadmaps for electrification for cars or aeroplanes. Electrification of transportation is happening. We need that if we're going to get a sustained reduction in CO2 emissions and to make a world which is both quieter and cleaner. And if we're going to do that, technology development is still needed. Power electronics and electrical machines are key to that. And there's some fantastic things we might do in the future. I always like the idea of the Jetsons and being able to fly around in electric vehicles in three-dimensional space. Tricky, but we'll get there one day. So on that point, I'd like to thank you all for listening and hand back to Marco to facilitate the debate and discussion.
Okay, thank you, Pat. Can you stop sharing your screen, please?
Maybe.
Thank you, Pat. Thank you for your presentation. Now I would like to introduce our panelists that we have in order to comment this presentation that we have from from Professor Patrick Wheeler. We have here in this, as was advertised, we have Bolin Sarlioglu, who is a professor at University of Wisconsin-Madison. I hope that I pronounce well your name, Bulent.
Yes, that's correct.
It's correct. He works with the Wisconsin Electric Machines and Power Electronics Consortium. His research areas are motors and drives, including high-speed electric machines, novel electric machines, and application of wide bandgap devices to power electronics in order to increase the efficiency and power density, something that that Pat spoke a little bit in his presentation. The other panelist I would like to introduce is Fernando Briz. He is a full professor in the Department of Electrical, Electronics, and Computer and Systems Engineering in the University of Oviedo in Spain. And his research interests include electric drives, electronic power converters, grid-type power converters mainly, control systems, and digital signal processing. I would like you Bulent and Fernando, to comment the presentation of Pat, please, and in order to share your views about these trends that Pat showed us in this morning here. As you wish, Bulent, if you can start, would be nice.
Thank you very much. Professor Wheeler did an excellent presentation, and he showed very interesting and also very current information that I haven't seen before in terms of the impact of COVID-19. Certainly, we are in challenging times right now, but humanity always overcome these difficulties in the history, and we will overcome this difficulties that we are experiencing right now. So, and we've got to have a future-looking vision on how the transportation industry will evolve. As a scientist, engineer, academician, working in the area of power electronics and machines, we are actually in very nice spot because of the electrification of electric vehicles, aerospace, trains, drones, a lot of other applications. So we should have a good vision to increase the power density for many applications, such as aerospace is kilowatt per kilogram. In the case of electric vehicles, the important thing is liters, the volume, kilowatt per liter, because the passenger space is important, as well as the cost, kilowatt per dollar or euro or whatever the currency we are using. So there are interesting opportunities for us in Wisconsin. Right now, we are working on wide bandgap based technologies. We are looking into implementing silicon carbide in many different motor drive applications. We have projects that we are working on in the area of current source inverters. Current source inverters are dual of VSI, and we are minimizing the DC link inductance using the capability of high switching capability of silicon carbide devices. In the area of electric machines, like our colleague showed, there are very good opportunities to increase the power density, like Professor Wheeler showed, 4 megawatt machine. It's very, very small. It's a high-speed machine. So as researchers, engineers, we can focus on that area as well, try to find the best magnet, best steel, best winding structure, machine topology, and we can contribute to humanity by developing technologies in the area of electric machines and power electronics. Certainly, there are other areas like controls, energy storage, wiring of the aircraft or the vehicle, and things like that. So, so that's my initial impression about Professor Wheeler's presentation, and I'm happy to see the developments both in Europe and as well as in all over the world in this area. So I'll stop here and give the opportunity to my other colleague from Spain.
Thank you, Bulent. Fernando?
Okay, thank you very much. Thank you. Can you hear me?
Yes.
Yes, okay, thank you. So thank you very much for the presentation and for the opportunity to be here. So it's a very interesting presentation. So I would say that now the issue is, so the technology is the same as 3 months ago. Now the question is, the world is the same as 3 months ago? Obviously the answer is not. Then the question is, how long will it take to the world to recover, yes, the kind of the normal behavior? So in opinion of Pat, it will be a matter of a few months. Really, I think that is the big discussion. Is a matter of a few months or a matter of years, or will never be the same? There will be kind of permanent changes. So I think this disturbance is bigger than anyone before. Perhaps we have to go back to the Second World War to find something similar. Okay, it's not a war, but the impact on the economy is similar size. So what will happen in the future? First, it will depend strongly on whether we have a vaccine or not. That will determine what will happen in the next months. But with or without a vaccine, the question is, there will be kind of permanent changes in our habits, in our behaviors, or not? The thing is the big question to answer. And regarding what is going to happen in the next few months, or perhaps more than 1 year, I think the impact is going to be bigger than Pat said. I'm thinking just in air transportation. So let's say all the major events this year, sports or cultural, tourism, whatever, they have been canceled. So we are talking just, let's say, a major city in the world like New York, Paris, London receives in the range of 50 to 60 million tourists. Okay, that is totally canceled. The Olympic Games is 500,000, is canceled too. The Football World Cup is 3 million. Let's see what happened in 2 years, but it's difficult to foresee. So, I mean, we are talking about 100 million people who are not taking planes. So I think the impact on air transportation is going to be huge during this year. I've seen some predictions. We talk about in the range of 50 to 60% of decrease. So for air transportation, it's going to be huge. For other means of transportation will be different. Train, I don't think is such a big deal. Will be interesting to see what happens with vehicles, with private vehicles, because now we all are working from our houses. So teaching is done, online. We work online. We are shopping online. So it will be interesting to see how fast we come back to our presential kind of habits. So my point is, the technology is the same. The importance of the technology is the same. We need to develop more efficient motors, more compact, higher power density. I totally agree with that, but I'm not sure if the world will be the same.
Thank you, Fernando. You spoke about the impacts that this pandemic, COVID-19, is having around the economics, that a lot of things are canceling around the world. So my concern about the conclusion that Professor Wheeler mentioned about this situation is that it will not affect the regular trend on some or less of the development of electrical technology for mobility, for the development on aircraft. My question is, Professor Wheeler, if you can comment about the things that Fernando and Bulent mentioned. Do you think there will be an impact over the investment for developing these technologies, especially on aircraft? What do you think about that? I mean, the investment, the fundings.
Oh, right. Well, okay. I'll get onto the investment part in a second. One of the things that interested me about this when I started looking into it is just over the last 3 months, how little impact the pandemic has had on CO2 emissions. And then when you start thinking about it, you realize that we're all still eating, we're all still consuming, we're all still buying technology for our computers. And this is all being flown around the world. So I agree, we're not all going to go and fly to the Football World Cup, but that's a blip. That's a small percentage of the CO2 emissions. Factories are still working and producing things. We're still producing food, and that food is still being transported. One of the things I noticed here is actually, I take the thing about not going shopping, but all my neighbors are having things delivered to their houses. So the number of trucks coming into my road and delivering things is very, very high. So is there still a need to look at transportation electrification? Oh, yes. Is it going to be the same mix as before? So are people going to be going to the Olympic Games and the World Cup and things like that? Who knows? But that doesn't necessarily have a massive reduction on the amount of need for transportation. It might change the mix. It might be that we need to focus more on goods because people will prefer to have them delivered to their house, certainly over the next couple of years. But you still need to have that transportation electrification if you want to reduce the impact of transport on CO2 emissions. And you have to do all the other things to reduce that as well, particularly in the electrical power generation world. There's no point having electric cars if you're going to use coal-fired power stations to charge them. I did go back to the World War II, I noticed that was mentioned, and actually back to what happened with CO2 emissions in the last pandemic, which was the Spanish flu, back about just over 100 years ago. And the interesting thing was that the reduction of CO2 emissions from the 2008 economic crisis was greater than it was for that pandemic all that time ago, even in percentage terms. So it's the economic impact you have to look at and manage. In terms of investment, what we're beginning to see in the UK is governments trying to invest in industry, to support industry and to make them look forward. Now, I don't know how this is in other countries. There's plenty of people here who will know in their own nations, but we're certainly seeing a lot of initiatives from the UK government to accelerate those projects that help companies take new ideas and develop those to higher technology readiness levels for industry. So I think that some governments may try and invest their way out of this, which gives a great platform for new technologies. So those are my thoughts on that. I'm not an economist, so I wouldn't like to predict the exact impact on the economy. That's why I took that chart from a very, very, very well-known international accountancy company, who I assumed at least has some ideas of economic modelling. And it was interesting to me that the sources I looked at weren't predicting recovery times of more than 2 years. And in terms of getting transportation electrification, we're looking at 2 decades. So maybe we've got a little bit more time to get there, but my view is we've still got to do that work.
Okay, thank you, Professor Wheeler. Professor Bulent, do you have any comments about that, about what is happening now in the US?
So in US, is like everywhere else, certainly we have challenges, but we are doing our best to open up the economy. And like Fernando mentioned, that once the vaccine or the treatment comes, things will get back to normal. I do agree with Professor Wheeler that we've got to have long vision rather than short blip. To me, this is a short blip in the history of humankind, and things may quickly get back to normal once the vaccine shows up. And so I work in aerospace industry, developing technologies for aircraft, new aircraft like 787, A380, A350 takes years, you know. So we have to invest our time right now to develop technologies for, 5-year, 10-year, 15-year horizons. So it's better to look at the big picture and see where we are going at, and we should have also positive thinking, right? If we think negatively, we stay negative. So I like to think positive and have a positive energy to go forward. Even though we have challenges, it's better to invest our energy and time as engineers, as academicians, to train our students and train our workforce to develop these new technologies. I saw one question also here about maybe you can ask, we've got to do a lot of studies, right? DC versus AC, or power transfer in the big systems like aircraft, as well as increasing the power densities, fault redundancy, different kind of machines, power electronics. So as academicians, PhD students, master students, there are a lot of opportunities to look at those technologies and come up with new ideas. If you want to make this aircraft or hybrid, we've got to compete with the fuel-based aircraft. So we have a lot of things to do to increase the power density. So my mind is always on the science and engineering part of the things. How can we think, make things better? Like Pat Wheeler said, we are not economists or policymakers. We don't focus on that area. But I hope that we will overcome this difficulty. That's my thinking.
Thank you, Professor Bulent. Now we have I will mention I will do the question from the attendance, okay, from the people that is attending this webinar. Okay, the first question, maybe I would like you to answer this, Professor Fernando. Mm-hmm. Regarding the development of electric system and aircraft, do you think the trend will be on the development of pure DC distribution generation system, or there might be a space for hybrid configuration? For instance, AC, DC microgrids on board microgrids. What do you think?
Well, I would say that this is not my field. I've seen a bit more on ships, but I would say that when you talk about high power systems, when you move in the range of the megawatts, the trend is towards the DC everything. It's DC kind of power distribution, and then you transform to whatever is needed by the actuator from the different systems.
Okay, Professor Wheeler, do you have an opinion of this question?
The weight and the losses, well, what causes the weight of an AC system when you start looking at higher powers, particularly for aircraft systems, means that you will go to DC for propulsion systems. The thing that's stopped DC becoming more prevalent on aircraft in recent years has been about the protection mainly and the fault scenarios. With solid state devices, we can begin to overcome those problems. And so therefore, I'm seeing the advantages of a DC system for propulsion being definitely the way it comes in. For civil aircraft, so for passenger aircraft, I think there'll be a hybrid system for a long time to come. The main reason being the pressure from the airlines and the aircraft operators to have backward compatibility with certain bits of equipment. So it's not a technological reason, it'll be a commercial reason. But when we're looking at new systems like high voltage propulsion systems, I think they are going to go DC. They're lighter, they're simpler, and they have more advantages in terms of efficiency. So that's certainly where I see them going. And that's good news if you're into power electronics, because then you're going to need power electronics to control motors, whatever happens. So that's my opinion, and it's certainly based on the studies we've done.
Thank you, Professor Wheeler. Another question for Professor Bulent. Do you visualize an Hyperloop transportation system working across America in the near future?
That's a very interesting question. And what Hyperloop system is, for those who don't know, maybe is a system where you have a kind of a vacuum, not 100% vacuum, but low pressure tunnel. And then you have like a train, almost like a subway going at, or Shinkansen, whatever you can think, going at very high speed. And the idea here is that you don't have the drag of the air, therefore you can spend less energy to move the vehicle. And so that's the idea. So we need to depressurize the tube tunnel, so that requires some energy, and then we can go fast. So that's the idea. So it is possible, and you can go very high speed, maybe more than 500 kilometers per hour. I saw the Japanese maglev going at that speed, which is impressive, at the Fuji Mountain testing facility. 500 kilometers per hour. It's very, very fast. So this is the same idea. So if this technology can happen, believe me, you know, there will be a shift from aerospace to maybe Hyperloop One kind of systems, where we don't have to wait at the airports, check in, and things like that. So it will simplify the you know, the way we do business. The other thing, it may change how we live. You know, if we have a very fast transportation system, the way the cities are built can change too. We can live outside of the city at least 3 hours by normal car and be there in like 20 minutes. So that changes the whole real estate market, whole, you know, thing. So can it happen in the United States? It can. It requires a large investment, and I also hear that this technology could be also viable for freight operations, meaning moving goods and, you know, goods essentially. So not humans, but you can ship whatever you want from one city to another in a very fast way. I do not know exactly what the status in US. There's certainly interest, but it's also competing with the auto industry, you know. So there are different stakeholders: aerospace, auto industry, Hyperloop One, and who's going to pay for this technology, and whether it's economically viable or not. We'll all see that in the future.
Thank you, Professor. I would like I have a question for Professor Fernando. What do you think we need to realize a big change in order to escalate the optimized model of these machines and power converters applied to transportation, aircraft or electric cars and so on?
What do we need to do to optimize?
Yeah, to escalate, because Professor Wheeler mentioned that it's easy to optimize, but the main problem, the main issue is to escalate these optimized models. What do we need, do you think, that we need to escalate these models, these optimized models of these technologies?
I'm not sure if I understand the right meaning of escalate. If we are talking about size, it's about that?
Well, I think
I'm not sure if we're talking about the size of the machine or power converter or about the volume of production.
I think I didn't misunderstand, but maybe Professor Wheeler can say that. But I understand that escalate refers to, in order to apply to something in the real, in a real situation. Am I correct, Professor Wheeler?
Well, the example I showed in the presentation was a very simple, relatively simple optimization of the aspect ratios associated with the machine, so the diameters and the length. When you actually want to start optimizing a system, say a propulsion system, you need to include models, scalable models of all the power electronics, the filters, the cabling, and so on. Ultimately, we need to get to the point where we can do an optimization of an entire aircraft based on what duty you want that aircraft to do. So that could be slower aircraft for freight, or it could be very fast aircraft for passengers high value passengers who want to travel very quickly, maybe even over short distances. So the optimization process is by no means complete. The one thing about that optimization that I was trying to express was it's not the optimization tool that is the problem. It is creating reliable, scalable models of the parts of the system to use within that optimization that's the problem. And the development over the next few years, to me, should be around how we develop those models, how we can create those models quickly, and how we can validate them quickly, so that we can do that optimization. And so that optimization problem will grow eventually to being a full aircraft. If you look at optimizing a full vehicle today using a computer optimization, you very quickly work out that it's going to take you 10 years just to create the models. So that's the problem. So I'm not sure if that answers your question, but that's certainly where I was trying to come from on that one.
What do you think about that, Professor Fernando?
Well, I think this can change. This can depend strongly on the application. So, for instance, you want to develop a car. How long does it take? The range of perhaps 4 years, 5 years, and since the very beginning to the very end. You want to develop the powertrain for a train, for a high-speed train. You have to do that in 1 year, only 1 year. What I mean is that kind of the level of optimization strongly depends on in which application you are working on. So I totally agree with what Pat said, but then the kind of the implementation or the constraints strongly depend on the applications and can be totally different for cars where you have massive production to high-speed trains where you produce a very few units for each model.
Okay, thank you. Another question, in this case for Professor Wheeler. What will be more relevant for power converters in transportation technology? The energy efficiency, I mean, decreasing the switching losses, or to achieve a better power quality, a lower THD, or a certain harmonics?
It's a good question because the optimization, if you take a power converter in an electrical machine, it's not just the size and weight of the power converter that's important, it's its impact on the system as a whole. So if you're looking at power electronics in an electrical machine, and then you look at the impact of the losses, for example, on weight, because of course output power quality to a motor means that that motor is going to have higher losses. That's your disadvantage. So the reason you might want a better quality waveform going to an electrical machine is to improve its efficiency. Now, the weight penalty for those losses can be different in an electrical motor to in your power electronics, or indeed to the whole power system of your vehicle or your platform. So you have to think about what those penalties are and therefore where you're going to put that optimized point. I've certainly worked on projects where the electrical motor designers get very unhappy because the optimum point puts more losses in the machine and less losses in the power electronics, simply because it's easy to cool an electrical machine sometimes because the materials are less sensitive to heat than some power electronics. The packaging of power semiconductors is very susceptible to high temperatures, and you're looking at getting heat out of a very small place. On an electrical machine, it's more distributed and it's in a naturally conductive environment for heat. So that balance is something you have to optimize, and you have to think about the whole problem, not just your part of it. Otherwise, you won't end up with the optimum system. So that would be my answer there, that you have to go through that and understand the weight penalty associated with the losses in each part of the system.
Thank you, Professor. A question for Professor Bulent, applied to the wide bandgap devices applied to transportation, and it's related to control schemes. The question says, some more sophisticated or advanced techniques for control power converters and machines, like predictive control, usually a final control set, or optimization techniques and artificial intelligence are not used today in the industry. Do you expect that will remain in the academia or can be developed in the industry of transportation? What do you think about that?
Very good question. So the controls, perhaps Professor Briz can also help me to answer this question. So I want to just start with this silicon carbide technology is not a pipe dream, it's reality. It's already being used at the Tesla Model 3 as a in the vehicle producing 100 kilowatt and more. So it's already in production, which is great for us to see as a scientist and engineers, right? So regarding control, there are challenges with silicon carbide technology where the control engineers can help. One of the challenges that we have is using very high switching frequency and high-speed motors. And for electric vehicle application, what this means is that we have to sample the current or voltage, DC link voltage and the phase currents. And then if we are switching fast, then we have to calculate, do the old control algorithms, predictive control or field-oriented control, and output the PWM to output to the inverter command. So if we are switching at 20 kilohertz, we have 50 microseconds to do all this. Sample, bring to the DSP, calculate, and output. But if we go 100 kilohertz switching, then we have how much? Divide that by 5, so we have only 4 microseconds, if I'm correct. So 4 microseconds, we got to do everything. So there are challenges with the control, how fast we can run the DSP and how fast we can minimize the time delays in the system. So that's one challenge. And regarding predictive control or deadbeat control, these are all good control topologies that allow us perhaps to reduce the losses both in the inverter as well as in the machine, and also increase the dynamic response. So there are definitely opportunities for us to implement those. But my observation is that at universities, we develop technologies. How do we get these technologies to the hands of engineers in industry to implement? That's the challenge that we have. So we have to pay attention to make webinars, short courses, workshops, and try to educate the current workforce that are working on those industries right now so that they understand what's a predictive control. They understand what's the artificial intelligence. And then once they feel comfortable, they can adapt those technologies in their vehicles. Also, the companies like DSP makers, like digital signal processing DSPs, if you can educate the engineers there, and if they start writing white papers and educate the, again, working workforce, then all these things that we are doing at the universities will permeate to the real life. Artificial intelligence, that's also very important. These autonomous vehicles are becoming important, and there are opportunities to implement electric motors, power electronics with autonomous vehicles. Therefore, there are opportunities there as well, but I'm not an expert in artificial intelligence, so I cannot talk much. So with that, maybe Fernando can help.
Professor Fernando, yes?
Yeah, sure. So regarding the silicon carbide devices or wave band devices, they provide 3 advantages, which is temperature, switching frequency, and breakdown voltage. So let's say you have to use one of those characteristics just to justify their use, okay? So if you focus on the switching frequency, it strongly depends on the applications. For instance, for electric drives, normally you don't need a very high switching frequency because the machine itself has a filter there, has inductance. But for power converters, yes, it can be a big advantage because you reduce the passives in the inductances. So I would say silicon carbide devices, they are now a fashion. But in some cases, I don't think they are justified. Why in other cases, they are enabling technology. I mean, you can do something that without them, without the switching frequency or the breakdown voltage, you couldn't do. So in those cases, definitely you have to use them. And then about predictive control, I think it's being used. However, I would say that at least for industry, let's say the way they think is try to do it simple. And if it doesn't work, do something more difficult. So most of electric drives, they can operate with very simple controllers, just PI, linear controllers, everything, and works very nicely. So in that case, what's the point of using predictive control? Really, I don't think it's justified. However, when you push the drive, the normal controls can fail. For instance, that drives operating at very, very high speeds, where the speed is close to the switching frequency, or high power drives with very low switching frequency, there are very few commutations, then in those cases, the normal controls begin to fail. They don't perform properly. So in those cases, of course, you can use predictive control. It's a very good option, or feed forward, that kind of things. So I would say predictive control has a field of application, but it's not the regular drive. Just look for something more specific. And then this kind of artificial intelligence, really, I don't see that for this kind of systems in which you can use kind of simpler methods which perform very nicely. So I would say you don't need it. Don't try to do it simple, and if it fails, just look for something more difficult. But first, try to do it simple.
Thank you, Professor Fernando. A question for Professor Wheeler. Given the importance of electromobility for the world, especially during this situation about COVID-19, what do you think about the interaction and the cooperation at international level about the different research groups around the world that are working about this subject, this topic?
I think we're doing very well, and a good example of that would be today. I don't know how many people have been listening to this, but for an online event, we've had a very large audience. So my first reaction to that would be actually the current situation where a lot of us are, or nearly all of us are home working, is providing an opportunity to try out these tools, to do more seminars like this, and to get better cooperation. It's not a good long-term solution, but it's certainly giving opportunities to spread information in ways that we haven't done before, and to audiences that are certainly larger than I would expect to see online before the pandemic. So we need to maintain those links. If we're in a situation where we can't fly and we can't travel so freely, around Europe, around our regions and around the globe, then that does present challenges for research cooperation in the way we've done it before. But I think the tools to work online have helped that, and we're all becoming more familiar with them, and we've got to take advantages of that. But we've also got to encourage our governments to continue to invest in the types of funding models that help both academia and industry to collaborate globally. And I hope people will take some of the models that have been used for the COVID-19 understanding, where a lot of countries were very open and very communicative, and apply that in other technology areas, so that when we're developing the basic technologies, we do continue and enhance our collaborations, not just in transportation and electrification, but in a wide range of application areas. I think that's important. Different regions have different needs, however. Since this is being hosted in Chile, Chile has a lot of challenges with long distance travel and with mining. In the UK, the distances that you can drive between cities in Chile take you from one end of our country to another. So the final implementations are going to be different. And it's in those places that different countries will have different competitive edges and different opportunities. But the basic technologies, we should be collaborating, and we need to make sure we use all the tools available to us, not just aeroplanes, to be able to do that. So I don't know if that answers your question, but that's...
No, yes, you did. Thank you, Professor. In the same field, I have a question I would like to know your point of view from the United States and from Spain as well. We have a lot of participants from Latin America, Colombia, Paraguay, Chile, Argentina, and so on. And what do you think? Do you think that Latin America universities research is ready to assume the challenges to change to sustainable mobility, especially referring to, I mean, well, in general, to electromobility? Do you think that how we are doing, how do you see that we are doing here in Latin America, you know? What do you see from United States? And then I would like to know about how do you see us from Spain as well?
Great question. So I had a chance to visit Chile as well as Brazil in Latin America so far. So I have great colleagues, you know, a lot of good researchers, good, very capable and reputable professor colleagues that I have. And the student enthusiasm is great. I've seen the facilities both in Chile and Brazil. They are state of the art. And again, the student enthusiasm and students willing to learn and adapt is very good. English is very good. So I see things very, very nice from the academic perspective. Like Professor Wheeler mentioned, Chile is a big country. I flew from Santiago to Porto Varas. You need to take an airplane. Same in Brazil, right? So it's a very big country, and I'm sure other countries are need transportation. So the aerospace is key. So this downturn is, in my opinion, is temporary. We do need aircrafts, and aircrafts is our future at the moment. Hyperloop, one concept is good, but it will take years to adapt that. If it can change the way we do transportation. But the aerospace is needed for countries like Chile and also Argentina and Brazil. Also for us to go Europe and Asia. So hopefully we can get back to normal as quickly as we can. And we can start going conferences and workshops and also exchange students, professors, so we are all on this as a humanity to develop the science, further the science and technology.
Thank you, Professor.
So can you hear me?
Yes.
Yeah, okay, yes. So I would say, so we have had a lot of contacts with Chile, with Brazil, also Mexico. So I would say that the level of their universities, of the researchers in my field is really high. And also considering, the situation of the industry in these countries, I would say is unusually high. I mean, you can see some researchers from Chile with a really high reputation, while in Chile, really, you don't have big industries in this field. So it's kind of amazing what they are doing. The same for Brazil is different, but also they have some very high quality research. So I would say also Argentina, so Inés Valle is here. So I would say for these countries, I would say that the level of the research groups in the field of drives and power electronics is really high, considering in absolute terms, but mainly considering the situation of the industry in those countries. It's really remarkable, the merits.
Okay, thank you. We have more or less 4 questions more, about 10 minutes more, okay? Well, I have a question that is I think it is applied to the main field of Professor Wheeler. And the question mentions that what will be the main applications that, according to you, will have the modular multi-level matrix converter in the near future?
Good grief. Modular multi-level matrix converters are a great topology and a very interesting topology when you want to start looking at modulation problems and the topology problems. I only see those being used really in applications where you've got high voltage, high power AC loads, such as very large motor drives, when you're operating off an AC grid. And as we said earlier, on an aircraft, we're looking at probably having a DC grid. But yeah, large based utility applications, I can see where you're using some big motors yeah, maybe in crushing rocks in mines, for example, or very large production facilities. That's the sort of place where you start to get those large drives with those very, very large topologies, where the advantages of the breaking the voltage down outweigh the cost of doing that. And you already see that. Yaskawa have a product in that kind of area with those sorts of topologies. And I'm sure the sort of things that Robicon was looking at many years ago, and ABB, Siemens already sell multi-level motor drives into those sorts of applications. So that's where I would see that happening, not in transportation electrification at the moment.
Okay, thank you. A hybrid propulsion, someone mentions about the hybrid propulsion and the question is about the regenerative braking. Does it exist? Does it apply to transportation applications? I don't know. Who do you think? Whatever of you. I mean, Professor Bulent or Professor Fernando.
What's the question
regenerative braking?
If maybe I think I understand the question. So this was in hybrid, particularly in the hybrid propulsion system, about whether you get regeneration of electrical energy into some sort of storage. Is that correct?
Yeah, well, it doesn't mention more details about the question was about that. I mean, hybrid propulsion,
so when
it doesn't mention about the storage or something. Maybe you can guide us about that.
Depends on the duty cycles you're going to see on the different parts of the system and how you design that system. But there's certainly, from my point of view, if you're going to say a hybrid aircraft, you would certainly want to put some energy storage in there, because even if you've got a gas turbine, you'd like that gas turbine to be as small as possible, i.e. to service the average energy requirement, not the peaks. So you're going to want some battery energy storage or something similar to take out the peaks. And then when you've got some troughs in the requirement, when you've got some low points in the requirement for energy, you're going to want to recapture that energy and store it. So I would say that just in the same way as hybrid electric cars, when you move to hybrid electric aircraft, you are going to want to regenerate electrical energy into that battery energy storage or something similar. And that's certainly possible. And they've been doing this in Formula One cars for years, where you have either inertia or electrical storage of energy. When you're braking, you regenerate, and when you're accelerating, you put that back in. That's how a lot of hybrid cars work, and that's exactly the same for aircraft. That's my opinion. I don't know if Bulent has similar.
And I think also the question can be interpreted as like, if we are descending on an aircraft, can we use the propellers as a means, as a wind, like a wind generator, to regenerate back energy and feed into the batteries? You know, do you have any? I didn't have any practical experience. I never have a chance to look how much regeneration can happen. I know you are working actively on this area. Do you have any insights how much regen can occur due to the descent? Certainly it depends on the angle of descending and everything.
Certainly you can recover some energy through that phase, and certainly you might want to think about how, or there's lots of complications there about what state you want the battery in when you get on the ground, and whether you're just going to use the windmilling of the fan to generate energy, or whether you're actually going to use the gas turbine as well to put energy into to generate energy through that phase of flight. Why might you want to do that? Well, if you're landing at a remote airport and you're wanting to turn around quickly, you might want your battery full of electrical energy to assist the takeoff and climb phases of your flight. So the answer to your question is yes, we have done studies which have looked at that, but also you might also be wanting to take energy from your gas turbine in a hybrid aircraft at the same time. So you might be wanting more than you can generate just using the prop.
Sure.
Thank you.
Just one comment. I would say in general, any hybrid system, whenever you have a power converter and an electric machine, they by definition, they are bidirectional. So they have the capability to regenerate. So then it's a matter whether you want to use it and you have some place to put the energy. But the system itself, once you have the power converter and the machine, you can regenerate.
Thank you. Marco?
Okay, well, thank you very much, Professor Wheeler, Professor Burent, and Fernando, for all this very interesting discussion. Thank you also for all the questions from the audience. Now I would like to open the microphone for a few seconds. If there is any comment, any question regarding this presentation, you had the chance to talk now from directly from your computer. Okay, I will give the microphone now to Cristina.
Hi. So, hi everyone. Thank you for this interesting chat. I think we have learned so much today. So thank you for your assistance, for your participation too, because it's been a highly rate of participation. Thank you to the speakers, Mr. Barlow, Mr. Sagliu, Mr. Breeze, and Mr. Wheeler. And yes, we would like to, well, Marco is sharing the screen now. I think he's doing. We would like to invite you to the next session, sorry, who will take place on 2nd June. And well, we really hope you we will join us again, right, to this next session. I don't know if Marco can share the room. Yeah, if not, I will read it. Yeah, here you are. So the main speaker will be Mr. Reed, who is the manager of distribution at CAC. Also, we will have as speakers Mr. Riddell, who is the innovation engineer manager at Transelec, and Rodrigo Palma, who is within the Solar Energy Research Center here in Chile. And the talk would be energy supply and services in time of COVID. So we really hope you register when you receive the invitation, who would be shortly. Thank you. Marco.
Thank you very much, Cristina. Okay, for now we are finishing the second session of these online meetings. And I would like to kindly invite you for the next session, which will be 2nd of June. This one will be in Spanish. We will be iterating every 2 weeks with Spanish and English sessions, so you are invited to participate. This is for now. I would like to ask you to activate your cameras just to take the screenshots for the registration of this meeting. And I would like to say goodbye to everyone. Okay?
Okay. Goodbye and thank you.
Thank you. Thank you, Professor. Thank you, everyone.
Thank you very much.
Bye. Thank you, everyone. Thank you, everyone. Thank you.
Thank you.
Thank you,
Bye-bye.
everyone.
Soon, bye.
Stay safe.
Thank you. Bye-bye. Bye-bye.
Thanks, Professor Wheeler.
Bye-bye.
Thank you very much.
And everybody.
Bye.
Bye.
Bye now.
Bye-bye.
Bye.
Bye-bye.
Bye. Bye-bye.
Hola.
Bye.
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 Thanks.
Okay.